Hello everybody and welcome to Chapter 3. We're going to be talking about descriptive measures in this chapter. By descriptive measures, we've been talking in Chapter 1 about collecting our data. If you recall, we talked about some of the data classifications and the way that we look at data collection and the methods for making sure that we collect that data fairly by using random samples. In Chapter 2, we organized our data and we were able to graph and put it in tables and get some sort of idea of what's happening with our data to tell a story about it. In Chapter 3, what's new is that we need a way to describe this data. And when we say describe the data, we talk about numerical measures. And there are certain kinds of numerical measures that are used to measure data. That is, we look at all of the data at once. If we just see a mass of numbers, well, you're right. What do we have to do? Well, one of the first measures that we have to look at is what measures the center. And the center of the data, we usually think of something called an average. There are many types of things that fall under the heading of the word average, but we're going to look at three of the major ones that come up every time we talk about statistical measures of the center. The most common one that most people know about is called a mean. Now, most people, when they think of the word average, we think of the average as being we sometimes call this the arithmetic mean. And I'll write that right here. An arithmetic mean is a mean by which we take the sum of all of the terms, all of the data points in our data set under a variable, arithmetic mean, and we add them up. And then we divide by the number of measures in there. Most people are actually very aware of this. If you have a grade point average, you have a type of arithmetic mean. Actually, you have a weighted arithmetic mean based on the number of points, quality points and GPA that you have, right? Each course is worth a different set of credits, right? So you take the number of credits times the grade and divide by the total number of credits. Still, it's a kind of a mean. And so the mean of the data set is the sum of the observations divided by the number of observations. Another measure of center that most people are commonly aware of is called a median. The median is when we take the data and arrange it in order. So we go from smallest to largest, increasing order. And then we look for the middle number. In this case, if there's an odd number of observations, it's really easy. We just find the middle piece of data and we're done, right? So right here, if we look for an odd number of pieces of data, if we have 95 pieces of data, right, our piece of data that's right in the center is going to be the 45th one. Oh, sorry, 47th one. But if we have a number of observations that's even, then what we're going to do is we're going to take the two middle observations, add them together and get their mean, and we consider that to be the median of that data set. So it's a little bit different if we're talking about an odd number of pieces of data or an even number of pieces of data. But in both cases, what we're looking for is the n+1 divided by 2 number in the data list. So we call that a median. Another measure of center, so-called center, is called a mode. And a mode is when no frequency occurs more than once. We could say that no mode exists, but a mode is the one that occurs the most frequently. And we can actually use the mode when we're talking about different things like data sets that contain names. We can actually find the most frequently occurring name. But it's the only kind of measure of center, so quote-unquote center, that we can use with that kind of data set, right? There is no mean of names or median. Those are all numerical. But a mean, a median, and mode can all exist with numerical data, and that's our focus. Let's consider an example here briefly. Let's say that we have the two data sets, right? We have a data set right here that contains 16 values. That's an even number of pieces of data right here, right? 1, 2, 3, 4, 5, 9, and 13. Good Lord, sorry. 3 times 4, 12 plus 1, 13. So this is an odd number of pieces of data right here, right? So if we did our job, right, the main thing you have to do, right, what many people forget to do when they're asked to find something about the mean or the median or the mode, is to first take that data set and order it. So let's order that data set right here. From smallest to largest, it looks like our smallest data set piece of data here is 300, right? And that occurs 1, twice, 3 times, 4 times, 5 times, and 6 times. So we're going to have 306 times in our data set right here. I'll write that out for us. 1, 2, 3, 4, 5, 6 times. We look at our data set, we look for the next highest values, putting them in order. Looks like 400 occurs twice right there. So we'll go to 400 and 400. Then we see next up is going to be 450. That also occurs twice, 450 and 450. Whatever these data points represent, looks like money of some sort. As we go along, we just simply go in an increasing order until we've got them all listed out. 800, 940, and then 1050. So if we wanted to get the mean, what we would do is we would add up all of these observations and then divide by the total, and there's 13 observations, right? So we would write n equals 13, 13 observations. N represents the number of data points in our data set. So if we take the sum of our observations divided by 13, we would find that the mean of this particular data set is $483.85. To find the mode, we would look for the very middle number right here. Since we've got 13, we're going to take 13 plus 1, divide by 2, that's equal to 7, right? And if we go to the 7th piece of data right here, here it is, that 7th piece of data is $400, and sure enough, that is our median. And of course, the mode, the one that occurs most frequently, is our $300. We see that occurred 6 times, so we consider these our main measures. In data set 2, there's an even set of numbers right here. It's just one less piece of data than we had over here, really. So if we were to go through and get rid of one of these pieces of data, like it looks like in that data set, we get rid of the $800 set, right? What we would have to do is our median would shift to be right in between these two middles. So if we wanted to find this median, all we're doing is we would add our two middle numbers, 300 and 400, and divide it by 2. Of course, 300 plus 400 divided by 2, 700 divided by 2, $350. 300 is still our median, or is our mode, and our mean this time becomes 474. Alright, so finding the mean, median, and mode is relatively easy, and I think most people are relatively familiar with that. There is a relationship between mean and median when it comes to certain kinds of data sets. When we look at numerical data sets, if we were to arrange them in a histogram, if the median is higher than the mean, it typically means that there's a right skew. If the mean and the median are exactly the same, or at least very close to the same, we would consider those to be a symmetric data set. In a left skew data set, the median is actually higher than the mean. So in these cases right here, we can actually determine some sort of relationship about the skewness of the data by looking at the median versus the mean of that data. The sample mean we're going to represent using this formula right here. It says the sample mean, we use the variable x bar, so we put an x, a little bar over an x, that's going to mean a sample mean. So from our sample, we get a mean by taking the sum, so this is the Greek letter sigma. That Greek letter sigma, x sub I, so each x sub I is an observation. We get the sum of all observations divided by n, which is our sample size, and that's going to give us our sample mean. The other measure that we want to take care of is called the measures of variation, and the measures of variation tell us how widespread the data is, how far spread out is everything. So, for example, let's consider these two basketball teams, right? There's 5 players on both teams right here. The average height in both of these teams is 76 inches, right? The average is 76 inches. But if we look at the data right here, we see that for the first team here in white, look at the spread of that data. Very very close to each other, right? The minimum is 72 inches, the highest is 78 inches, while on the opposing team right here, we have a low of 67 inches and a high of 84 inches. There's much more variation in the second team. And one way to tell variation immediately is to use what we call the range, and that is, let's look at the highest and the lowest. In the first team, the highest was 78, the lowest 72. The difference is 6 inches, whereas in the second team, the highest is 84 and the lowest is 67. That's a difference of 17 inches. We call that range, and a range of a data set is one measure of the spread. It's called maximum minus minimum. If we know these two values, that's one measure. Now, it's a bit of a crude measure because sometimes we can have data that we call outliers that are way too high or way too low as compared to the rest of the data. Another measure that we use is called a sample standard deviation, and in another video I'm going to show you how to use this formula. It looks a bit complex, but it's sort of a, if you follow a cookbook kind of method for doing this, if you wanted to do it by hand, you can do that. I'm going to show you the method. But a sample standard deviation is found by taking this sum and dividing it by n-1 as their square root. All kinds of fun things going on in there. We'll use that formula shortly. The main thing I want you to see is that variation in the standard deviation is that the more variation there is in a data set, the larger its standard deviation. And an example is in order right here. I'm going to use this formula right here. We're going to calculate our standard deviation using this formula right here. I'm not going to go through all the math, but I'll show you what happened when I did this. Let's say in data set 1 and data set 2, I have two data sets, both with an average of 50. But if I look at the data set's standard deviation from data set 1 and the standard deviation data set 2, we can see that data set 2 has a much larger standard deviation. And sure enough, our data, when we see it in this ordered values, goes from smallest to largest right here. And that difference is huge, 20 to 70, that's a 40-inch difference, whereas the data set 1, the data set had a range that only went from, let's see, 66 minus 41 is going to be 25 inches, right? And you'll see that the data surrounding our middle value tends to spread out, right? Fairly evenly in both cases, but if we look at the data set right here, we see that that spread is not as large as when we look at this data set down here, right? And we see that, wow, even inside of the data set, the data is there's a lot of variation going on right here. And again, visually, what we've done is we've taken all of our observations and made a dot plot of those. So see last week's video on chapter 2 for that. In these dot plot videos, you can see that we are within one standard deviation. If we take the mean and we start adding or subtracting the standard deviation to that mean, we're not very far spread out in this data set, right? You see that the green dots only occur within maybe 2 standard deviations at the most above our mean, right? That's sort of an outlier almost. Whereas for the second data set, our standard deviation of 14 points is really big. And all of our data is very far spread out. So this measure of standard deviation is a way of getting this picture of how far spread out our data is. There's one rule that you do want to know right here. We call it a 3 standard deviations rule. We say that almost all observations in any data set will lie within 3 standard deviations to either side of the mean. So if you look at our 3 standard deviation rule, right, we see that none of the data falls within 3 standard deviations of the mean, right? Just about all of the data, we're actually going to say if it's normally distributed data, 99.7% of the data always falls within 3 times the standard deviation away from the mean. That means if I took my standard deviation, added it to my mean 3 times to the right, this was 3 standard deviations or 3 times to the left, I'm going to get that difference right there. So almost all of my data should fall in. Another quick note would be that if we had 2 standard deviations to the left and the right, any data point that falls outside of that is considered kind of unusually high or unusually low as compared to the rest of the data, right? And we see that we do in fact have a couple of unusually high or unusually low pieces of data in this data set too. So in my next video, I'm going to show you how we actually do this. We're going to use a hand method, and then I'm going to show you how it's calculated using Excel.